This is the other problem from homework last week, and it's about the zoo that is collecting entries to name a new baby elephant. And if you noticed, what we have here is the number of entries in the box after noon is modeled by the differentiable function e from 0 to 8. Now, notice that e is measured in hundreds of entries. So this would be 400, this would be 1300, this would be 2100, this would be 2300. I also think it's a really good idea to sketch a graph so that you really can keep track of what the y and the x-axis are. So this is the number of entries. Okay, this is the number of entries. So if we look at this table of values, we're going to just approximate the rate, which have been deposited at t equals 6. Okay, now 6 is not given. We don't know what the total is at 6. So we're going to look between 5 and 7 here, and we're going to just see what the change would be. Okay, so if we do that, we notice here that e at 7, e minus e at 5 over 7 minus 5, and this is just an average rate of change, but we're going to use that to estimate the instantaneous rate of change at 6. And the total change is 800, okay, is 800 over a 2-hour time period. So that's how we get 400 entries per hour. Now, in letter B, this 1 over 8 of 0 to 8, this is actually, remember, the average value. So it's 1 over b minus a of a to b of the integral of et dt. Okay, so we're trying to find the average value of e. Okay, notice there's a big difference here between part A, which is an average rate of change, and then in part B, we're looking for the average value. Okay, so here, when we finally get this integral, it is the average number of hundreds, right, because our scale is hundreds here, of entries in the box between noon and 8 p.m. And it's very important on the AP exam that you say what the units are and be sure to restate what the time interval is here. So you need to give an indication of what this whole value means, but be sure to state the limits here of integration. Now, in part C, what's happening now is that at 8 p.m., okay, at 8 p.m., they've collected all of the entries that they're going to. And then the volunteers start to process those entries. Okay, so they start to process those entries. And this is the rate at which they are being processed. So they're opening the mail, they're looking at the entries, and they're going to do that from 8 until midnight. Okay, so in part C then, at 8 o'clock, there were 2,300. And then we're going to subtract how many hundred they process. And if you integrate that function p of t, then you'll notice that that would be 700 entries left. Okay, 700 entries left. Now, notice that they rewrote this, but they just use p of t instead of writing the full equation. All right, now in letter D, this problem is asking us to find out when the entries are being processed the most quickly. Okay, and if you remember, when we're looking for an absolute max or an absolute min, we always want to check our endpoints, and then we also want to check any values where the derivative is 0, because those are our relative maxes and mins. relative maxes and mins are candidates for absolute maxes and mins. Okay. Now, I did this a little bit differently. Okay. I put the function in here as y1, and then I changed my window, and I went from 8 to 12, and from 0 to 20. Okay, from 0 to 20. And if I graph it, you can see this nice graph here. And if you look at this graph, if this is a graph of the rate, you can see right away that the rate has a maximum value at, this is at 12. All right, so this is at 8, 9, 10, 11, and 12. Now, the reason that we find the derivative is because this is a local max, this is a local min, and once again, those are candidates for absolutes. Okay, so these two values here, this turns out to be a local max, this is a local min, but the absolute max turned out to be at 12.